Welcome back to the Bleeding Agent channel. No preamble today. We are skipping the pleasantries because, frankly, we have a crisis on our hands. We're drowning in silos.
It's the Tower of Babel problem all over again, isn't it?
It is exactly that. I mean, look at the landscape right now. You've got brilliant engineers building incredible agents in LangGraph, another team over in Crew AI, some enterprise architects wrestling with semantic kernel.
And the Google folks on ADK.
Right. And they're all building these amazing systems, but none of them can talk to each other.
Not without bespoke, brittle, total nightmare API integrations. You're basically writing custom wrappers for every single interaction. It's that n-squared integration problem.
Yeah, if you have 5 agents, you need 20 connections. If you have 10, you're writing code until next Christmas.
It's just not scalable.
Right, and that is not an internet of agents. That is a series of walled gardens. So today we are tearing down the walls. We are doing a deep dive into the agent-to-agent protocol, A2A.
This is the big one. This is the attempt to standardize the wire.
Our mission today is pretty simple. We are going to dissect the architecture of A2A, strip away all the marketing fluff, and figure out if this is actually the TCP/IP for the agentic web, or, just another standard that's going to collect dust. And just a quick tone check for everyone listening. This is not a beginner's guide. We assume you know your LLMs from your microservices. If you don't know what a schema is or why race conditions matter, maybe turn back now.
Fair warning, we're going straight into the specs today.
Okay, let's unpack this. Give us the technical definition. What is A2A? And please don't tell me it's a framework.
It is definitely not a framework. So technically speaking, A2A is an open standard protocol. And this is crucial. It was originally developed by Google, but it has now been donated to the Linux Foundation.
So it's vendor neutral.
Completely. And it's designed specifically to facilitate communication between independent, opaque agent systems.
Opaque is a key word there that I want to fight you on in a minute, but first, break down the stack. How is this thing structured?
Well, it follows a layered architecture, sort of like the OSI model, but simplified for agents. You have 3 main layers. Layer 1 is the data model.
The nouns.
Exactly. The protocol-agnostic definitions. What is a task? What is a message? What does an agent card actually look like? Now, here's the interesting engineering choice. These are all defined via protocol buffers.
Okay, pause there. Why protobufs? Why not just stick with JSON schemas like everybody else in the REST world? It feels a little heavy-handed.
I get that. It's about strictness and, polyglot support.
Yeah.
If you are building a massive agentic mesh, you're going to have Python agents talking to Java backends, talking to Go services. JSON is flexible, but it's loose.
Too loose.
Way too loose. Protobufs enforce strict typing. If a Python agent sends a task object, a Java agent needs to know exactly byte for byte what that structure is. You don't want serialization errors when an agent is 3 hours into a reasoning task.
Fair point. Reliability over flexibility at the data layer. Okay, what's layer 2?
Layer 2 is operations. These are the abstract capabilities. Send message, get task, cancel task, the verbs.
In layer 3 must be the transport.
The bindings. Yeah. This is where the rubber meets the road. The spec explicitly supports JSON RPC, gRPC over HTTP2 with TLS, and of course, standard HTTP plus JSON REST.
Okay, so as an architect, I have to ask, why the split? Why support both gRPC and REST? Isn't that just adding complexity to the spec for no reason?
It's all about the trade-off between efficiency and ubiquity. If you're running internal agents inside a Kubernetes cluster, you want gRPC. It's binary, it's low latency, it supports streaming natively.
Right.
But if you want to expose an agent to the public web or to a partner who's running some legacy stack, you need REST. You need to be able to hit it with a curl command.
So it tries to be the best of both worlds.
It effectively decouples the what from the how.
Okay. I want to circle back to that concept of opaque execution, because coming from a monolithic background or even just standard microservices, we're used to having some insight into the other service. We want observability.
Right. And in A2A, the remote agent is a complete black box. Unlike local sub-agents, think of a LangGraph workflow where everything shares memory. And state A2A agents do not share internal state. They don't share memory. They communicate strictly through their declared interfaces.
Okay, playing devil's advocate here, that sounds like a debugging nightmare. If I'm running a Python agent on ADK and I call your Java agent and your agent starts hallucinating or gets stuck in a loop, I can't see its chain of thought. I can't see the prompt. I'm just sitting there waiting. How is that better?
It's better because it enforces the contract. In properly distributed system, you shouldn't know how the other service works. You should only care about the input and the output. If you rely on knowing my internal prompt structure, we are tightly coupled.
So if you change your prompt, you break my agent.
Exactly. I break your agent. By treating me as a black box, we decouple our life cycles completely.
So it prevents me from building a system that relies on your implementation details.
Precisely. You care about the interface and the outcome. If I hallucinate, that's my bug to fix, not your architectural flaw.
That leads us directly to the engineering value prop. Because right now, the alternative is, what? If I want my agent to talk to another agent, I usually just wrap the second agent up as a tool.
Yes.
I say, here is a function call. Go do the thing.
And that is the agent exposure problem. When you wrap a complex stateful agent as a simple tool, you are stripping away its agency. You're treating it as a stateless function. Input X, give me output Y.
But agents aren't stateless functions. That's the whole point of them.
Exactly. They shouldn't be.
Yeah.
The value prop of A2A is that it allows agents to be exposed as agents. This means they can maintain their own state. They can manage complex multi-turn workflows. They can handle long-running operations LROs without the calling agent needing to sit there and manage the execution loop.
Let's contextualize that for the listener. We've all been there. You have a Lambda function acting as your controller. It calls GPT-4. It waits and waits. And then at the 15-minute mark, the Lambda just times out. The execution is dead.
A2A totally solves that. You initiate the task, you get a task ID back, and you disconnect. The remote agent keeps working. It maintains its own state. You can check back later, or it notifies you. You aren't paying for compute just to wait for a token stream.
That is a game changer. If I hand off a task to a specialized coding agent, I don't want to micromanage every line of code it writes. I want to say, build this module and have it come back when it's done, or if it needs my input.
And because it's protocol-based, you get that interoperability we mentioned earlier. You can connect a Python agent to a legacy Java service or a LangChain agent to a semantic kernel agent, as long as they speak the protocol.
What about security? I mean, if we're opening up these black boxes to talk to each other, that sounds like a massive attack surface. If I expose my internal agent to the web, aren't I just inviting prompt injection attacks?
Well, it's designed to be secure and opaque. Identity is handled down at the transport layer -TLS 1.3 and up, HTTPS. Authentication uses standard headers like OAuth 2.0 or OIDC. But the real key is that the agents act as gatekeepers.
Yeah.
They don't expose their internal tools or databases to the caller. They only expose the high-level skill.
So I can't SQL inject your agent's memory. I can only ask it to perform a skill it has already advertised.
Correct. You're authenticating against the intent of the agent, not its underlying infrastructure.
All right, let's get into the architecture deep dive. How does this actually work step by step? If I want to find your agent, how do I even know it exists? It all starts with discovery, right?
It does. The entry point for everything is the agent card. Think of it as a JSON metadata document.
The business card of the bot world.
Essentially, yeah, but a business card that defines the rules of engagement. There are two main ways to find these. First, there's the well-known URI you just hit, .wellknownagent-card.json on a domain.
Standard web practice, RFC 8615. Same way I find your SSL info or your security.txt file.
Exactly. Or, for enterprise use, you have curated registries, central repositories for cataloging. But the interesting part is what's inside the card. It lists identity, service endpoints, auth schemes, but crucially, it lists capabilities and skills.
Capabilities like what?
Things like streaming support or push notifications, and skills define the input and output modes. Can this agent handle files? Does it accept a JSON schema as input or just natural language text?
Okay, so my agent finds your agent's card, it likes what it sees. Walk me through the request lifecycle. It's not just a simple GET request, is it?
No, it's a full handshake. Step 1, the client fetches the agent card, parses the security schemes, and then gets a token out of band, usually via a standard OAuth flow. Step 2, initiation. The client sends a send message request.
And here's where it gets really interesting, because the response isn't always just, here's your answer.
Right. If it's a trivial query, like what time is it, you might get a stateless message, an immediate reply. But for complex work, you get a stateful task. It returns a task object with a unique ID and a context id.
And that task object has a lifecycle. This is the state machine part.
It's a standard state machine. It goes from submitted to working. But here's the really cool part. It can go into a state called input required.
Why is input required so important?
Because in the real world, agents get stuck. Maybe the prompt was ambiguous. Maybe it needs approval to spend money. Input required allows the agent to pause its own execution, signal the caller, hey, I need a human or a clarification, receive that new input, and then resume.
So it handles human-in-the-loop natively?
Natively, yeah, without breaking the connection or losing state.
That is massive. Most API integrations just fail hard there. You get a 400 error and you have to start all over. Here, the task is persistent.
Exactly. And when it finally finishes, the output isn't just a text string. It's a structured artifact. And an artifact is composed of parts, a text part, a file part, a data part. You can pass entire files via bytes or even URI references.
Now let's talk about the bleeding edge stuff, asynchronicity. We all know LLMs can be slow. If I have an agent doing deep research, I can't have an HTTP connection hanging open for 45 minutes.
No way. A2A handles this in two ways. First, there's streaming via service-send events, or SSE. This is for real-time feedback, like token streaming. The server sends task status update event and task artifact update event over persistent HTTP connection.
But what about the really disconnected scenario? Mobile clients, serverless functions that time out, or just really long jobs like write me a whole novel.
That's where push notifications come in. This is designed to solve the polling problem. Instead of your client asking, "Are you done yet?" every 5 seconds.
Which is so inefficient.
Totally. The client sends a push notification config that contains a webhook URL and a token. When the task updates, the server posts to that webhook.
Whoa, hold on. Webhooks. That sounds like a security hole the size of a truck. If I expose a webhook, anyone on the internet can spam it. I could get a fake update saying task failed or send money here. How do we trust that callback?
That is the #1 fear with webhooks, and A2A addresses it directly with cryptography. The server doesn't just send a plain JSON blob. It generates a JWT, a JSON web token, signed with its own private key.
So it's signed.
Yeah. Yes. And because you have the agent card from the beginning, you have the location of the server's JWKS, its public key set. Your client receives the webhook, grabs the JWT, verifies the signature against a public key, and only then does it process the update.
Okay, so that completely prevents the fake update attack vector. You know with cryptographic certainty that the update actually came from the agent you hired.
It is essential for zero-trust environments. Without that signature, webhooks are basically unusable in an enterprise setting.
Now we have to address the elephant in the room, or the other protocol in the room, MCP, Model Context Protocol. I see people confusing A2A and MCP constantly. Are they competitors? Are we going to see a format war like VHS versus beta?
No, and this is the most critical distinction to make. If you take nothing else away from this deep dive, take this. They are complementary. MCP standardizes agent-to-tool connections.
Tool being the keyword.
Right? MCP is stateless. It's for specific functions like query a database, read a file, or take a screenshot. It's about expanding the context window of a single model. A2A standardizes agent-to-agent connections. It's stateful. It's about delegating high-level goals.
You had a great analogy for this from the docs, the auto repair shop. Let's walk through that.
Sure. Think of a mechanic agent. When that mechanic needs to check the engine codes, it picks up a diagnostic scanner. That scanner is a tool. It doesn't have agency. It doesn't think. The interface between the mechanic and the scanner is MCP.
Okay, so MCP is for using the wrench.
Exactly. But now, the mechanic realizes the alternator is dead. They don't manufacture alternators, they need to get one. So they call the parts supplier agent.
And the parts supplier isn't a tool, it's a whole other business.
Correct. It has its own logic, its own inventory, its own business hours. The mechanic says, "I need an alternator for a 2015 Honda." The supplier agent might reply, "I have one, but it's in the other warehouse, it'll take 2 hours." That negotiation, that delegation of a complex goal, happens over A2A.
So MCP is for extending your own body. A2A is for talking to other people.
That is a perfect way to put it.
Let's talk about extensibility. Protocols usually die when they become too rigid. If I need to pass some custom data that isn't in the specs, say a specific compliance ID for a banking transaction, am I just out of luck?
No, the protocol is designed to be extensible. You can use URI-based extension flags in the agent card and also in the headers. It's designed to allow extra data without breaking the parsers of agents that don't understand that specific extension.
Give me a concrete example, not a theoretical one.
Okay, look at Twilio. They're betting big on this. They built a latency extension. In voice AI, latency is everything. If an agent takes 4 seconds to think, the human on the other end hangs up.
The dreaded dead air.
Right.
Yeah.
So Twilio's agents broadcast their current latency in the A2A header using an extension. The calling router can see that before it assigns the task. It can say, okay, agent A is overloaded with 500 meters latency, but agent B is at 100 meters. I'm routing the call to agent B.
That's incredibly smart. So the protocol itself carries operational metadata, not just the task payload.
Exactly. And because it's an extension, if I'm a simple text bot and I don't care about latency, I just ignore that header. Nothing breaks.
So adoption. We've seen protocols launch with huge fanfare and then just die in a GitHub repo. Is this actually happening, or is this just Google trying to make fetch happen?
The momentum is real, and I think the move to the Linux Foundation was the signal that changed the game. It isn't just a Google project anymore, it's vendor neutral. We are talking about over 150 organizations now.
But are they actually shipping code, or just putting their logo on a website?
They're shipping. Salesforce and ServiceNow are building what they call Agent Fabric to connect all their disparate enterprise bots. They realize that no single company will build every agent an enterprise needs. AWS and Cisco are integrating it. On the consumer side, you have Uber and S&P Global.
And for the developers listening who are using ADK, the Agent Development Kit, this is just baked in.
Oh yeah, it's native support. In ADK, you can turn a local agent into an A2A server just by adding a decorator or changing a config. You expose it. And conversely, you can consume a remote agent using Remote A2 Agent as a client proxy. You can deploy these to Cloud Run, Kubernetes, or Agent Engine. It handles all the plumbing, the serialization, the handshake, so you can just focus on the logic.
Let's look forward. 5 years from now, if A2A wins, if this actually becomes the TCP/IP of agents, what does the ecosystem look like? Because right now, I still have to hard code your URL into my agent to call you.
That's the phase 1 implementation. In 5 years, we move to dynamic swarms. We move away from hard-coded integrations entirely.
Meaning my agent doesn't know who it's going to call until it actually needs them.
Exactly. Imagine a gig economy for bots.
Yeah.
Your agent encounters a problem, say it needs a complex legal contract reviewed. It doesn't have a legal module, so it goes out to a curated registry, queries. I need a legal agent, specialization in IP law, with a reputation score above 4.8.
So it discovers, vets, and then hires the agent completely on the fly.
Yes, but that requires immense trust. You aren't just calling an API endpoint, you are conducting business.
Which brings us to the blockchain stuff. I saw the Ethereum proposal, ERC 8004. Is this just crypto hype, or is there a real use case here?
It's a real use case, but specifically for identity. If I'm going to pay an agent microcents to run a task, and I've never met the developer, I need a trust layer that isn't owned by Google or Amazon. We're heading toward on-chain registries for identity and validation. This enables what some people are calling identity machines.
Explain that term.
It enables zero-trust handshakes. Agents transacting across organizational boundaries without a pre-signed legal contract, verifying each other's reputation and public keys on-chain before they even start talking.
That is the true Internet of Agents, a mesh network where specialized agents, legal, coding, procurement form, ad hoc teams, to solve problems the user didn't even know were complex.
It changes the entire paradigm, from building a chatbot to architecting a digital workforce. You aren't building a monolithic brain anymore, you're building a manager that knows how to outsource effectively.
Okay, we're coming up on time. I want to leave our listeners with the one thing they absolutely need to remember. What is the one killer feature of A2A?
For me, it has to be task immutability and state management. A2A doesn't just pass messages. It creates a shared, trackable unit of work, the task. That task object survives network blips. It supports human intervention. It gives you a persistent handle on a complex operation that might take hours or even days.
That's the difference between a toy and a tool. A toy breaks when the Wi-Fi flickers. A tool remembers what it was doing.
It really is. If you aren't thinking about how your agent talks to other agents, you're building a legacy silo.
And nobody wants to be the architect of a silo in 2026. A massive thank you to our expert for connecting all the dots today. And to you, the learner, the architect, the developers, start looking at your stack. Are your agents lonely? Maybe it's time they made some friends. Keep building, keep leading. We'll catch you on the next deep dive.